So Sundar Vedantham, he's a senior technical manager working in the data center group in Allentown. His research interests include the network traffic and congestion management, high-speed networking, and theoretical computer models, areas in which he holds patents and has published papers, book chapter, and articles. You have to reference for those books.
Oh, yeah. It's on a Google search away.
Yeah, so he received his Ph.D. in computer science from Louisiana State University. He enjoys writing articles in English and Tamil. Okay, you're a writer as well. Okay, to help improve public understanding of technical details behind the field he has worked on and to attract young students to get into STEM.
Thank you so much. I appreciate it. I'm glad that I'm following the right sequence. What we are going to talk about is improving core performance when packets come in. So we've been talking about DPDK a lot. DPDK can get you a lot of packets from the network interface to the cores really, really fast. But once you get to the core, usually there are 3 different kinds of scheduling that you need to do to get the processing done properly. So in the slide set that I had, I was trying to so we'll talk about multi-core applications, and then why do we need eventdev, and a little bit of eventdev theory, followed by API application and the code availability and your takeaway, right? So I wanted to actually move like slide 17 to the top, but since it's being live streamed, the slides are all already up there on the web, so we couldn't move that around. So I was just writing this down. So when you have a lot of packets that are coming in that need to be processed, usually they fall into 3 different categories, the way that needs to get processed. The first one is parallel. So this is the beautiful wall, right? What MJ was describing this morning, like where you don't need any cache coherency, individual packets that are coming in are self-contained and you process it and you are done and it moves on, right? And not only that, the packets can come in and go in any order, it doesn't matter. So if the packet flow is like that, it's beautiful, it's wonderful, and it's very easy to manage. And if you have a lot of packets coming in, you can put more cores and you can load balance it across. And the scheduler just needs to look at which core is free and keep shipping packets, and you'll get linearly increasing performance as you throw more cores at it, right? But I come from the telecom world, and the tier 1 telecom vendors that we usually work with, if you look at the 5G, 4G kind of traffic profiles, 80–90% of the traffic does not fall under this category. So they either fall into one or both. In the ordered case, the FIFO order is important. So the packets that come in need to be processed and then pushed out in the same order, right? And then we have atomic flow, where there can only be one packet that can be processed at any given time from one flow, right? What it means is you are, let's say, touching some table, database, manipulating it in some way or another as a part of processing that packet, and that's going to result in some change that will affect subsequent packets that are coming in that same flow. So you cannot have 2 packets from the same flow being processed by 2 different cores, 2 different threads at the same time, and that's going to put the whole thing out of whack. It's not going to work, right? So to do this, of course, in software, it's probably pretty simple. You just put a memory lock around the shared memory region and then send them out, and so you can serialize and get this behavior. But if you do that, then it's automatically performance is going to nosedive, right? It's not going to work properly at all. And in the ordered queue also, you may have multiple cores, logical cores, real cores, and you get packets processed, but when they come out, depending upon what kind of workload each one of the packets had, the packets may come out of order, and so you need a way to rearrange them, put them back in the order. So Unfortunately, 80–90% of the traffic falls into this category, and this could also be due to the fact that if these properties are inherent, automatically programming becomes really easy, right? You don't need to really worry about something going out of whack if the system somehow ensures that packets are always going to be in and out in the same order and you're not going to mess up any database. That's where all the cache coherence, those kinds of things come into play. So when it comes to multi-core processing, what do? We do two kinds of models that we have been talking about. So one is run to completion. So in this case, you have each one of the core practically running the same code. It does the same stuff. So we have the traffic coming in, maybe packets received, firewall, flow classifier, metering, routing, all this takes place, and then packets get pushed out, right? Just as a sample case. So each one of the code does the same thing. In that case, you can think that the scheduler can send the packet to any one of the available cores, and you can get nice load balancing. That's very true if it's all parallel queue packets, right? But in our case, if the traffic is mostly ordered and particularly atomic, what naturally happens is you send one packet that belongs to an atomic queue to this core, and then before it gets processed, if another packet comes in, you end up sending it to the same core, and then the third packet comes in while the first packet might have been processed and pushed out. Now you got the second packet in the same core's queue, so you need to put the third packet into the same core, right? So pretty soon you realize you have multiple cores, but your flow gets pinned into one particular core, and you're not able to move that away from the core for a while. So as a result, load imbalance across cores is often seen. That's a big problem. Of course, it has cache locality advantage, and flow atomicity is automatically supported. That's all great, right? But so how do you solve that problem? So the other approach is pipeline processing. So in this case, you break down what needs to be done into multiple Cs and load it up on different cores and then pipeline it around. So that's all well and good. It automatically ensures FIFO order because there is only one flow, and it ensures atomicity also because maybe only one particular section of the code needs atomicity and it always gets done in one flow, so no issues, right? That's fantastic. But the problem is most of the time the what needs to be done in each pipeline stage is not going to be exactly equal. So in some area it's going to be a lot of work, in some other stage of the pipeline it's going to be a lot less, and again you are going to skew the load across different cores, and whichever core has to do more work becomes the bottleneck slowing down the whole flow. So what we are trying to do in eventdev is to have the cake and eat it too, right? We want both. So eventdev, which is event device, is a scheduling model. It's basically a library inside DPDK. So it tries to address the shortcomings of both these models. The idea is to improve the core utilization to the maximum extent possible, and also provide support to address dynamic load balancing. So in the pipeline model, if your flow or like what you need to do with the packet is just one flow, and if it never changes, fantastic, great. But often things are going to change. There are different traffic coming in, different flows needed. And so if you set up just one pipeline, it's pretty difficult to re-architect it depending upon dynamic flow changes, right? So we are trying to address that also here. And simultaneously provide atomicity and packet ordering capabilities built into the design itself. But the couple of beautiful things about this implementation is eventdev is available as a library in DPDK, but it's not really dependent upon any one particular processor or a hardware feature or anything like that, right? So actually, Cavium is coming up with their own hardware scheduler. So eventdev can run on top of that, right? In other processors, if there is no such hardware accelerator, there is already a software-based scheduling code available, so that can run on top of that. So whatever device that you have, you can run it with or without, and if there are better, smarter, newer hardware load managers that come in, then eventdev can take advantage of it and give you better performance. Right. So how does that work? What's the idea behind? Right? So in this case, you have the RxQ from the NIC traffic coming in that goes into a particular core that sucks in the traffic. Then that's going to give it to the eventdev scheduler. Then the scheduler is going to look across all the cores. The cores could be real cores, but in all the discussion, we call it a logical core, meaning it's basically a software implemented core, right? So each real core may have multiple cores depending upon what is it that you are trying to do. So there could be one thread that's running one kind of processing and another thread doing another kind of processing, and depending upon what you want to do, you can send it to any one of the available cores. Right, so the packet comes in, it comes into the eventdev scheduler. It's going to look at all the cores across and then send it to any one of the cores that's least loaded that's capable of handling this particular load or the particular packet that needs to be processed. The interesting thing is, once the code receives and then handles the packet, it has to come back to the event scheduler again to the same port, and then the event scheduler is the one that will actually put it out to the transmitting core, which will then send it out to the external world, right? So it cannot go out from the core directly to the PXQ. We'll see how it works in a little bit more detail later, but the basic idea is this looping around, bringing it back and giving it to the eventdev scheduler allows the eventdev scheduler to keep track of which core has which packet, and anything that's coming out of order, you can put it back in order to ensure ordered queue processing in the system, right? So because of that, you cannot send it out directly. It may look like it will be more efficient, faster to send the packet out directly, but then you cannot support ordered and atomicity kind of thing. So you need to always loop it back, and then the eventdev will send it out. What's the current status? It's already implemented. You have the code available. So as I said, it's one library inside the DPDK world. The idea was originally proposed by Aaron Jacob of Cavium. So worked with Intel and then NXP to get the implementation actually done. Now there are a lot of companies working together to improve the API. Intel did a lot of contribution also. So it is already checked in and it's available as part of late last year releases. And there is a SQM that stands for Software Queue Manager that's already been implemented and released to the DPDK GitHub. And so that scheduler is currently available. So you can run it on x86 cores and get this going. And there are sample applications that are already available to show how the load balancing works. So the device, the system, the sample code are all ready for people to take a look. Just a little bit of theory to see how the flow works. We actually have like a long tutorial that runs half a day, one day to take people through the whole sample application and building and so forth. But this one is just a half-an-hour thing. So I've tried to put a lot of links on the slide itself, and I've tried to keep the slides very easy to see from the last row, so there's not a lot of content. But if you look through the slide, you will see all the links and pointers to documentation that you can pick it up, right? So we need to talk about pipelines, and then the components inside the eventdev is like devices, ports, and queues. Then the different type of scheduling that we were just talking about, and then how do you link the ports to queues to get this functionality working. So pipelines. So pipelines, as we said, made up of these stages. Depending upon your application, eventdev itself doesn't really preclude you from designing the application any way you want. So the general idea is to take your entire process flow and chop it up in equal amount of CPU cycles that will be needed to get it done, right? So, and you can break it up in as many stages that sounds reasonable for your particular application. So one action gets performed in each one of the stage, and then it comes back to eventdev. It will send it to the next stage and loop it through until the process gets, then you send it out, right? That's the basic idea here. So it could be, for example, flow classification, firewall, ACL could all be one stage each if that's appropriate. The load balancing is across cores. The cores, in our case, is logical cores, and the logical cores perform all the work that needs to be done, right? And the idea is to make sure all cores have equal load. And how do you ensure that? Is by looking at the queue depth, the consumer queue depth across different logical cores to make sure they're all evenly loaded. So here is where the flow comes in. So it could be the traffic coming in. It could go through an atomic queue that's load balanced across 3 different cores. When it gets done, it can go back into another atomic queue. Again, can be load balanced across the same cores or different cores depending upon what threads, what processes that you have running. Then it gets pushed out. Right? The single link, a lot of documentation is there inside the DPDK world. It basically means you have like a pipe connected to the TX core that will push the traffic out. Right? So you can have a simple flow where the traffic comes in. Instead of having this atomic, all this flow, you can have a single thread that just goes through one core and comes back and goes out also. That's possible and supported. Yeah. That's where the scheduler comes in. So when it comes to this stage, this is, again, the eventdev is sitting here, right? So it can actually put the order back in form before it gets pushed out. That's exactly the reason why it needs to keep coming back to the eventdev scheduler before it gets pushed out, right? Exactly like you asked, if you don't have the stage, if it directly goes out, then it can go out of order and you can't guarantee. Right, so the whole setup is called a device, meaning the entire SOC or multiple L cores that are all running together. So a device is one instance of the eventdev pole mode driver inside DPDK. As I said, it could be a software-based one or a hardware scheduler, and the software PMD is available right now, right? And the ports and queues that we are talking about is all part of that one setup. So subsequently in all these slides, I'm trying to use just this one figure so you get this picture in your mind. So this whole thing is like one device, right? That's the eventdev that's running there. Basically, that's the scheduler. So you have from the NIC traffic coming in through a core, and then all these ports are all the eventdev ports. You can call it event port or something like that because they need not be physical ports in the system. So traffic comes in, and when the library is called, it's going to look through all the ports and then get a particular packet assigned to any one of the ports. So for example, in this case, it's an atomic queue, and it's load balanced across these 2 cores. So eventdev is going to look at the queue depth here, and then balance it across and put it on one of those. Right? And here, the core dequeues that particular packet. You can actually grab a bunch of packets, like we were talking about PPP and so forth, to amortize cost across multiple packets. And when it finishes processing, it has to put that back into the same port, right? And then this port 1 can send it to this Q2, and then eventdev will schedule it out to go to the TX port, right? This is the kind of the simplest representation, but you can imagine a lot more cores there and different set of cores being mapped together to get some particular function working, load balancing across this set of cores for one function and this set of cores for another function. So port, as we said, that's the interface between the actual logical course and the event dev, where packets come in, it gets picked up by the logical core, and each port is associated with one particular core, so that it picks it up. I keep saying core, so that's always L core, meaning it's one particular logical core that is taking traffic from the queue. So here you can see this port 1 is associated with core 1, and it's always just that one core, right? Queue, so each queue is a stage of a pipeline. So like we were saying, if there is like A, B, C, D stages, then you'll make them into multiple queues. And each queue can be load balanced across multiple logical cores as you would prefer. They all support this atomic, ordered, and parallel. So depending upon which kind of flow that you want, you would put them on that kind of queue. So that the queue is what holds the events that are coming in that need to be processed until a particular, any one of the logical cores can pick it up, becomes free, right? So we already talked about. So this is the scheduling mode that we talked about. So event dev scheduler itself automatically ensures that if you call something an atomic queue, atomic flow, it's going to make sure not more than one logical core holds that event during processing. Within that, there is a little bit of nuance. We'll talk about that next. Basically, if there is a huge set of instructions that need to be processed for one particular packet to be handled fully, it's basically within that logical core, it's run to completion model. But within that, the atomicity may be needed only for a subsection of the code. So you can put the limits just across that. So as soon as that part is done, you can issue a release, and that will free the event dev scheduler to assign one more event from the queue to any one of the available cores. So basically, you are reducing the amount of time you are holding up the other events that are in the queue. So linking queues and ports, and this is what basically maps what is waiting in one particular queue to any of the available ports. The ports can be linked to multiple ports. So this is what happens. So initially, you may have a setup like what the orange lines show. So dynamically, you can add a new link so that now this is getting load balanced across two ports, right? So this can be done dynamically. So depending upon what your application load is, at any given time, you have a huge number of logical ports available. You can keep adding, deleting to load balancing dynamically. The workers are the logical queue, logical cores that does the packet processing itself. So at any given time, if I am the logical core and I am free, I'm going to go look at the queue in front of me and then grab as many packets as I can. If I look at the queue ID, I'll get an understanding of where it's coming from. We'll look at that in a little bit of detail in the next slide. When I do the processing, once it's done, as per the application, I know where it's supposed to go. So I'm going to write the queue ID to go to the next stage, loop it back, put it in the same port, and then the event dev will pick it up and put it in there. So there is this RTE event structure. So it can handle like DPDK packets as well as the event dev event. So the same structure handles both kinds. It could be a pointer, it could be a buffer. So there is a 16-byte area in the packet. So where there is a 8-byte metadata, and then this 8-byte is part of the payload itself, right? So if you look at what it contains, the event metadata has multiple fields like flow ID, sub-event type. Most of them are used. There are a couple that are reserved at this point. But just looking at flow ID the operation type and priority, the PMD can figure out where it's supposed to go, right? So those 3 areas are enough for the schedule, the event dev to look at the packet and figure out where to put that next. So when you instantiate an event dev API, you'll go in this order. You'll instantiate a device configuration. You set up, then you set up all the ports, then link the ports as you want, and then get the device start and it will start processing. In runtime, this is the 3 items that we were talking about. So the receive cores, they are going to do new events. So when there are events coming in, and the worker cores are going to do the forward part, and then the transmitting core can do the release, right? So those are the 3 steps that are needed to get that going. The software PMD is available now to do the whole mode driver scheduling work at this point. It's all merged into event dev tree, and it's being released as part of 17.05 or any of the future DPDK releases. So in this one, you can see this NQ and DQ. These are responsibilities of the worker core. So worker core is going to suck the packets out, and then when it's done, it's going to NQ. The green ones pulling it up and then putting it in the right queue, and then dequeuing it across the ports that are load balanced. That's the work of the whole mode driver itself, right? And the main thing to note is that the performance comes from properly balancing it, right? So you do need to think through to see what model, how breaking the work into multiple stages of the pipeline for your application suits the need and what will work really well for you, etc. So the number of stages, cycles, simply creating more L cores is not going to help you more. There are a lot of monitoring tools related to cycles per packet, port bus distribution. Those are all available. In the tutorial kind of sessions, we walk through to see how the performance is and so forth. But there is enough documentation available on the web at this point. So number of stages, configure, cycle, those things. So get that running first, then you can tweak the parameters to get the thing working properly. The last 2 slides just list the resources that are available to you. So it's all in the dpdk.org site itself. So if you go in and dig in, you will find the sample application, all the demos, etc. Currently available. You can build it up, run it on any code you want, and then keep fine-tuning. The main takeaway is to ensure the balancing works by splitting your application up into the right size of stages and then the right set of core mapping to get that done. That's all I have to say. Any questions? Yes. Basically, as much as, yeah. Is there a limit on the number of cores? It's basically as many threads that you can spawn, right? So it's basically a parallel thread that's initiated. So event dev itself doesn't really post that kind of limit at this time. Definitely. I mean, it's just like if you take any of the even Intel processors, etc. It may have like 4 cores, but it may, if you do even like top kind of thing, you may see 10 cores because each one is running 2 threads to create 2 logical cores out of 1 physical core. So. Yeah, I mean this one is it's basically a software library. So the way we imagine it working is on the receive and transmit. Ideally, you may have individual cores, and then you can create a thread that's going to call the PMD over and over and then run it, right? And then you can instantiate as many logical cores as you want. So that's up to the designer himself herself. EventDev itself tries to stay away from dictating, putting any limits on that, or how many cores can be there, those things. Yep. It's on stream, so I guess we need to wrap up, but I'll be around. Any quick questions?
We heard about VPP. Do you guys envision this like dealing with one packet at a time, or is it like a vector of packets?
Within that logical core, it can be anything. So you can imagine a system where instead of a logical core, it's a real core, and it's actually sucking up 100 packets and processing it all in parallel, right? So that EventDev is not precluding that.
But the scheduling is with EventDev, right?
Yeah. So from the scheduling point of view, if you're like load balancing it across so many number of cores, it's going to keep putting it across that. So if you really want all of them to be VPP processed for a particular application, you can create just like a one core mask thing and send that over just for that process alone, for that application processing alone, right? So it's basically up to the application and the designer. If you want that all to be VPP centric and all processed in like bulk by one real core, that's fine. Then you can create a single path to that one. But still in the system, you can have other packets going to multiple cores and load balanced across, right?
So do you mean by that?
Sorry. Yeah.
We really have to stop time.
Okay.
You'll be around?
Yeah. Thank you so much.
No.